This is our project presentation for computational geometry project on implementing the art gallery problem. And so we will start with this. So this is our main.py file. Our group number is 25 and we will run it. So once we run the main.py file, we are presented with a very interactive user interface. What we are planning to do is solve the art gallery problem to model a farmland so that we can find out how to do smart agriculture. That is, we can find out the optimal places for placing our guards as sprinklers. So for irrigation purposes, it is very important that the sprinklers that we are placing, they cover maximum possible area. That's why this is one of the best use cases for solving the art gallery problem. So we will do a few use cases. We will try a few test cases for the same. So first of all, let's start with a very simple polygon. Let's start with a simple hexagon. So if I start with a simple hexagon and I close it, as I do that, now I will do a monotone partition. After doing a monotone partition, I can see that since it was already a monotone polygon, so the monotone partition is the same thing, and then we will triangulate it. After doing a triangulation, we can see that we have obtained the following triangles, and we have also performed a 3 coloring of the same. From doing 3 coloring, we can see the red vertex is the one with the minimum color. And so when I say show optimal sprinklers, so the sprinkler has to be placed around the red vertex because it is seeing a lot of the field area. Now we are allowing the user to check what kind of radius is required for the sprinkler to cover the complete polygon. So if you just expand the radius, you can see how much of your area is covered. This is the simplest polygon which we have tried, and now we will try a few other test cases similarly. So let's try another test case. Let's work with a more complex polygon this time. So let's have a polygon which has got some merge and split vertices. So this is one such polygon, and let's partition the polygon. So doing a partition of the polygon gives us into 3 pieces which are monotone within themselves. As we can see that we have found out the merge and split vertices and used the trapezoidalization algorithm to form the monotone pieces. And now we will triangulate and 3 color it. So these are the triangles which have been formed after monotone partitioning. And then again the 3 coloring gives us the vertex, and we will use the vertex with the least colored vertex as our guards, and based on that, when we say show optimal sprinklers, we again get the sprinklers around the vertex guards that are present in the polygon, and we can again adjust our radius to see how much of the field is covered. Also, since we can model, the user can model any kind of polygon the user likes, therefore all kinds of obstacles and everything have been covered within this, and the UI is very clean and intuitive, and we have provided that all the instructions which are required to do the same. So let's try a few complex test cases. So let's try a test case with more number of vertices. Let's say we take a test case which has about 15 vertices. So if I do, this is the closed polygon because it has to be a closed polygon, and then we partition it. After partitioning the polygon, it gets successfully partitioned into monotone pieces, and we 3 color it. Again we can see that the 3 coloring is perfectly performed, and when I say the sprinklers, I get the sprinklers around. I can again adjust the radius. Now based on adjusting the radius, I can see that certain areas are covered and certain are not covered, so I need to place certain sprinklers at certain other points for complete coverage. So let's move to some test cases with more than 20 vertices. So I run it again, and let's have a test case with, let's say, some 20 plus vertices. So I'll randomly make a polygon. I'm trying to make it as complex as possible with many split and merge vertices in total, and I close this polygon and I do a partition. As I do a partition, I again get the monotone pieces very perfectly. We can see that all the pieces that have been created are monotone within themselves, and again when I 3 color it, so I get the complete triangulation very clearly, and again I can see the guards where they have to be placed, and these guards I can again adjust the radius and check how much of a field is covered. So we can see that the vertex guards, because of the additional constraint, all the things are not getting covered, so we have to add certain other sprinklers there too. So let us try another complex example with as many pieces as we can. So let's do some working here. So I'll try to create a huge enough polygon this time and check how it works. So as I am creating a very complex structure here, this is something that completely tells us what kind of farmland it is, because farmlands can be of very complex shapes. And then I partition it, and the partition is again successfully created. So no matter how many vertices we have, we get really good monotone partitioning, and then we 3-color and we get proper triangles. And based on that, we again can see the sprinklers where they have to be placed. So this is our project. Thank you. Okay, so let's try one last example. So I'll again run the code. Let's try another example this time. So let's try again a large example, and here I am making that, and I close the polygon and I partition it, and it gets successfully partitioned as usual. And again I 3-color it. I can see all the triangles very clearly. I can see here, so when we use the stack algorithm, it checks for the convex vertex on the opposite side and then it joins. So all these things can be seen. We have used the DCEL structure and stuff like that to model all of these things, and we can see the sprinklers at their optimal points, and we can as usual model this, which is very beneficial for people who use the who will use our application to check the farmland and its structure. So this was our project. Thank you for understanding.